That was my favorite class this morning. You doing okay? Yeah? Today is Thursday, so we'll do Tuesday. This is reading quiz. What is this, 5, 6? 5? Oh, good. And then after this one, you don't have to take them anymore. So reading quiz 5, we'll have it on Tuesday. You don't have to because you dropped, like, you only need 5 quiz grades. We'll do...
Really good one.
I know. We'll do 103 up to 114. And that's going to be up to human production and detection of sound. All right. Let me send myself an email right quick. Just a second. Okay. We don't have a test for, what's today? It's the 7th?
Yes.
Yeah, so we have several weeks till the next test. We'll probably have another quiz before then, or maybe 2 more quizzes, I don't know. But we'll have that one on Tuesday. Good holiday, everybody? We went to Mississippi. We had a good time. We went up to Percy Quinn State Park and rented a cabin there. We usually get away from town because we live sort of right on the parade route or in between the parade route. And so about 1 weekend of parades is about all that we can take. But we went up there, had a good time, built a campfire, hung out, sort of just played around the park. Had a good time. Anybody been to Percy Quinn State Park? It's nice up there, no? It's a good park. I like it. It's one of our favorites. Yeah, had s'mores. We ate lots of junk food. Like that, when we go camping, we eat a lot of junk food. Had 2 king cakes, s'mores, Pop-Tarts, cookies, all sorts of stuff. It's like this huge feast. Let's pick up where we were last time. We were doing, wrapping up chapter, what was this, chapter 4? Chapter 3? Wrapping up chapter 3. And then we'll move on into chapter 4 today, which is sound and how we produce sound, how we receive and detect sound. So we talk about these different ways that we lose heat. And remember we said last time that radiation, that's your primary means of losing heat. That'll be followed by evaporation and then conduction and convection. So conduction and convection, this is going to be about 20% of your total heat loss is through conduction and convection. Now that doesn't include sweating. So I know that we said that sweating is really a process of conduction, but here this 20% is no sweating. Because we're putting that into the category for evaporation. So evaporation, which isn't really a form of heat loss, but we're listing here it as separate, is about 30%. Y'all follow what I'm saying? You have 3 methods of heat loss. They include conduction, convection, and radiation. But we group sweating in with conduction because when you have water on your skin and it evaporates, it takes energy away from your skin because it's in contact. So it's really a form of conduction. Okay, it's not a separate form of heat loss. But we're listing it separately here because it's such a huge way, or such a huge way for your body to lose heat. And then radiation is the remainder. This is about 50%. So this, for example, is why we use those, those space blankets. You know what I'm talking about? Like you see people at the end of races or people that are in disasters, and they have those really thin sort of aluminum foil type blankets. Because you lose so much heat by radiation, it keeps that heat in. Even though it's really thin, it's reflective. It reflects that infrared radiation back into your body, and you don't lose all of that. We'll see infrared radiation later, so I'll bring our infrared camera, and we'll see sort of how people look in the infrared. But just for now, just know that radiation is a major way that we lose heat through our body. Typically, body produces about 100 watts of heat. And remember that 1 watt is equivalent to 1 joule per second. And 100 watts, that's the same as a light bulb, like a 100-watt light bulb. And you know how hot a 100-watt light bulb is. You've seen an incandescent bulb, you try to touch it, it puts out a lot of heat. And the body is similar. We can affect our heat gain and our loss in a number of different ways. And your book goes through different ways that you can do this. Here are just 6 examples. You can take cool or hot showers. So like if you're working out and you get really hot, you come back and you take a cool shower, or maybe even a cold shower, and it just helps your body to cool down. Similarly, goodness bless you. You all right, Sydney? Yeah. Similarly, in the summertime, taking cool showers in the morning will just help your body to remain cool all day. So cold showers are a good thing. They can be really good for your body. Remember I told you about the Get Fit guy, this podcast? And he thinks, I'm not sure if there's any merit to this, but he thinks that taking cold showers, very, very cold, as cold as you can stand them, helps to lower your metabolism. Or not lower it, raise your metabolism, because your body has to heat up more. You can drink cold or hot liquids. So like people in the South are known for sitting around on the porch drinking sweet tea, cold tea, because it's so hot here in the summertime. It helps your body to cool down to drink cold liquids. And why people in the North are known for drinking hot liquids, coffee and tea, hot tea. You can insulate the body. This limits radiation, and it also limits convection. All right, a windbreaker, for example, limits the convection that occurs when a cool wind blows across your skin. 4, you can have forced convection. I remember when I was a kid, we didn't have air conditioning when I was a kid for a number of years. When I hit about 4th grade, we got air conditioning. But up until I was, what's 4th grade, 12, 11? Up until I was about 11, we didn't have air conditioning in Mississippi in the summertime. You know, it's like here. But I remember as a kid going up in front of the fan and just sometimes just sit there for 10, 15 minutes just trying to cool down. And then what do you do when you stand in front of a fan? So forced convection, like fans, for example. Evaporation, you don't have any control over this, but it's certainly something that your body does. Or you can have control over it. Sweating. You can use misters. For example, at the zoo, you've been to the New Orleans Zoo in the summertime. At a lot of the major turning points along the route of the zoo, they have misters, and that's pretty common in hot climates. It's a problem around here because evaporation isn't as effective as it is, say, in Colorado or somewhere where the humidity is a lot lower. So around here, when it's hot, it just gets kind of sticky, right? Like it feels sticky, and that's because the humidity is a lot lower. And when we sweat, the sweat doesn't evaporate as readily because the air is already saturated with water, and it just won't take on additional water. So sweating is certainly a lot less effective at climates like here in South Louisiana, just because the humidity is a lot lower. And it's a lot more effective, say, in Colorado, where the humidity is a lot lower. That's why they tell you to drink a lot, because you sweat, but you don't really know that you're sweating. When you sweat here, right, everybody knows it because you're dripping sweat down your face. It doesn't leave your body as readily. But when you're in a very dry climate, that sweat will go away quickly. That's why, too, in Louisiana, compared to, say, out west, where the humidity is a lot lower, they have a different way of cooling their homes. You know, how do they cool their homes in the west, where the humidity is a lot lower, huh? They use swamp coolers. You ever heard of a swamp cooler? It's sort of like the air conditioner that we have in between Beauregard and Pelcha Hall, that big noisy thing that you walk past. That's an evaporative cooling system, where you have water that comes up, and then it falls down these cascades, like these waterfalls, and as it falls, water evaporates, and it causes the temperature of the remaining water to cool down. And with a big evaporative cooling unit like the one between Pelcha and Beauregard Hall, you can get the water quite cold. I don't know, 40, 50 degrees Fahrenheit. And then they use that water to cool all these buildings. So the systems that they use to cool these buildings are quite a bit different than what you have in your home, which uses a freon-based system. This is a water-based system. They cool the water, and then they pipe that water all around the campus, or at least up here in the quadrangle, to cool these buildings. It's a lot cheaper than using a freon-based system and a lot more efficient. But out west, they have those on all the individual homes. So here you have a compressor that compresses the freon, and it goes through and cools off your house. But there they use water very much like here, where they pipe the water up to a cooling unit on top of your roof or out next to your house, and it falls down, evaporating along the way like in a little waterfall, cooling that water, and then comes back and cools your home in a similar way as what we do out here, but not this big. Like the unit's about the size of a normal AC unit, like you'd see. So anyway, evaporation is a very effective way to have heat loss. And then finally, radiation. As I said, your body radiates, so you can have heat loss. Or you can have heat gain through radiation. For example, with the sun. So the sun gives a lot of energy. It heats the earth, and it can heat our bodies as well. So if you go outside on a sunny day, then you gain a lot of heat because of that. Alrighty? So those are just different ways of heat gain and loss. Make sure that you know sort of how those work. I also want you to know how the body regulates its temperature. And then there are 3 different ways that it can regulate its temperature, where the brain actually causes this to occur in the body. The first is that blood vessels in the skin can contract. All right, is that going to cause your body to heat up or cool down? So the blood vessels on the surface of your skin will get smaller. Will that cause your body to heat up or cool down? Think about it. So if the blood vessels get smaller, that means there's less blood flowing to your skin. What will that cause you to do? Well, if less blood flows, what happens if blood flows to the skin? What happens to your skin? The heat leaves, right. And so if your blood vessels contract, what happens to your body? Does it cool or heat up? It heats up. So when your blood vessels in your skin contract, it keeps that blood sort of deeper down inside of your body, and you don't lose it as readily. So when blood vessels in the skin contract, you have less blood to the skin, and you have less heat loss. By the way, you can also have them dilate. Right? Contract means get smaller. Dilate means that you get bigger. Like your pupils dilate. They get big when you go to the eye doctor. And when they dilate, that's more blood to the skin and more heat loss. Always have to think about it. Okay, what's happening when the blood vessels contract? That's less blood to the skin, so I have less heat loss. And when the blood vessels dilate, then it's the opposite. These are all involuntary things. This is not something that you control necessarily, that you can't make this happen, but your brain can make it happen. 2, shivering. Usually involuntary, though I guess you could shiver on your own and it would have the same effect. Shivering produces heat. And then finally, your brain can release chemicals to increase your BMR. This is the whole motivation behind the Get Fit guy with the cold shower craze. That release chemicals to increase the BMR. That when your body's really cold, your brain will step in and say, hey, let's stoke the fires a little bit and get this person warmed up again. Release chemicals to increase BMR. Remember BMR, that's our basal metabolic rate. That's just the amount of energy that our body needs just to function. And that's in contrast to the total metabolic rate, or the TMR, which is the sum of BMR plus the energy that you use just for activities. So release chemicals, this produces heat. And then you have a number of voluntary things you can do. We listed some of those in that list of 6, right? You can take cold or hot showers, drink cold or hot liquids. You can change your clothing, what you're wearing, wear more clothing, wear less clothing, a number of voluntary things that you can do to regulate your temperature. Body's very, very good at regulating its temperature. That's why we always walk around with just, 98.6 or 37 degrees Celsius temperature in our body. We have some ways to enhance heat loss. I've already listed one of these, but we can have blood vessels dilate. And then also sweating. Remember, blood vessels dilate, they get bigger, opens up the floodgates, the blood flows up to the skin, and it heats up the surface of the skin, and then that heat is radiated out. And then sweating, of course, is evaporation, and then conduction is really wrapped up in that. Hyperthermia, that means that the body is too high, or the body temperature is too high. This can be caused by a couple of different things. You can have a fever. The fever helps to produce white blood cells. Which, can fight infection. So that kind of hyperthermia is quite good for your body, that if you have a high temperature, it can help you to produce white blood cells and then help you to fight off whatever it is that ails you. I know that when my wife and I get sick, let's see, which is it? Well, when I get sick, I tend to just get a really high fever, and sometimes I'm over it by the time the next morning. Like sometimes I'll just get sick in the middle of the night, and then by the time 7 or 8 o'clock rolls around, poof, I'm good to go, because that fever really helps your body to heal. But my wife, on the other hand, she might run a fever and she might not, but the result is that it tends to sort of linger for a lot longer. So it's good to have a fever, right? Sometimes it can be too high, but it can be good that it's a sign that your body is doing what it's supposed to be doing. And then the second thing that can cause hyperthermia is exertion, or high temperature, or dehydration, all of those. Talked about that in the video with the NFL football camp, how they said that their temperatures are usually a lot higher than normal. Gosh, I think, what was it, like 102, 103? Those football players, those NFL football players, because they're out in the heat and they're exerting themselves basically nonstop all day long with just a few breaks. So if they become dehydrated and they're not able to sweat properly or not able to cool their bodies properly, they can enter into this hyperthermia pretty quickly. Because they're exerting themselves in high temperature. And hypothermia is the body is too cold, or the body temperature is too low. And that's usually just due to environment. Alrighty? So know those different methods of heat loss for the body and how they work, the radiation, convection, and conduction, and then how the body regulates its temperature, both voluntary and involuntary ways that the body regulates its temperature. Let me show you something. I wanted to show it to you last time, but I forgot. And we'll talk about it next time, or I didn't have it last time. We'll talk about this later when we actually look at the in-body scanner in our electricity chapter, our chapter on electricity. You ever seen an in-body scanner? They might have one back in Alley Hill. They have one over at the rec center. As a student, you can use it. They might charge you a fee, but usually if you just ask them, they'll let you use it. It sort of looks like a scale, except there are two handles that you hang on to, and it puts an electric current through your body. You can't really feel it. It tingles maybe a little bit. But it puts an electric current through your body, and it does an analysis of what your body is made up of. What's lean mass, what's fat mass, what's water mass, and then it estimates your BMR. And I just show you this because this was mine from a number of years ago, about 5 years ago, where it has my total body weight. I'm a bit more than 153 now, but it shows my weight, and then there's my skeletal muscle mass, my fat mass. But at the time, I was running and cycling a lot, and I was having back issues. And at this time, in September of 14, I started lifting weights a lot. Or not a lot, but a few times a week. And so I want you to notice here, this is sort of pre-lifting weights. That my legs, they were all over. This isn't really me, by the way. Not me, it's just a picture. Okay? So my legs are over. That means that my legs were too heavy for my body. And the rest of my body was sort of normal. And then I also list my BMR. My BMR was about 722 calories, or kilocalories here, because we're talking about physics calories, not food calories. So 1722. And then in September, I started lifting, and then I did this again in May. And so you notice, first of all, that my weight went up about 10 pounds, 10 pounds. And now my legs are sort of normal, but then my upper body was over. So it's like my arms and my core had gotten disproportionately bigger than my legs. But the main thing I want you to point out here is the BMR, that's that basal metabolic rate, has now gone up almost 100 calories, which might not seem like much, but it's quite a bit to increase your BMR by that much. Now part of it is just that I'm heavier, that I required more BMR, that just my body needed more. But your muscle mass requires more energy to operate than other masses in your body. Alrighty, let's see, let's try some of this. Yeah, we can do this. Do the one on the left. A person sweats, and they sweat off 1/10 of a kilogram, 0.1 kilograms, that's 100 grams. So, what, about a third of a cup of water, probably. So if I sweat off 1/10 of a kilogram, how much heat is dissipated through this evaporation? And then I give you the specific heat, the latent heat of vaporization, and the latent heat of fusion of water. So you need to know which of those you'll need to use and how to use it. I'll remind you the equations that we had when we were talking about calorimetry. We had 3 equations. We had Q is equal to MC delta T, and then we also had Q is equal to M times L, and then that L was either our latent heat of vaporization or our latent heat of fusion. Those are both on your equation sheet. So the L here was either vaporization or fusion, latent heat of fusion or vaporization. All right, doing pretty well. Ask your neighbor what they put if you're not certain. Most of you have the right answer. Let's stop in about 10 seconds, okay? Stop at 153. 153. Really? Is that 28 people here? Yeah, I guess that's it. Okay, good job. B is right. To find this, I say Q is equal to the mass times the latent heat of vaporization. My mass is 0.1 kilograms. Latent heat of vaporization I give you right here, it's 500. kilocalories per kilogram. My kilograms cancel. I'm left with kilocalories. 0.1 times 500, that's 50 kilocalories. So that's how much heat is dissipated when you sweat moderately, not that much really. It's a lot of energy to take away from your body, a lot of heat energy. Hey, what's the, this is relevant since we're talking about food. What's the difference between roast beef and pea soup? You say, I don't know? Anybody can roast beef. You get it? But you can't pea soup. All right, let's try the one on the right here. It's a calorimetry problem, so using one of these two expressions, these two equations, but you need to know how to use it in the context. How much energy required to raise the temperature of 2 kilograms of water, 37 to 42? Oh, the C is our specific heat. All right. Many of you have the right answer. A few do not. So ask around. If you're ask your neighbors, you'll probably ask somebody with the right answer. All right, let's do about 8 more seconds. Stop at 155. 155. Okay, good. A is right. So here we're using our Q equals MC delta T. The reason I know I'm using this is because I have a change in temperature. I'm not changing phase. With the sweating, I was changing phase. I was evaporating, going from a liquid to a vapor or a gas. But here I'm not doing that. I'm just raising the temperature from 37 to 42. So I want to figure out the amount of energy. The mass is 2 kilograms. Specific heat is 1 kilocalorie per kilogram per degree Celsius times delta T. Delta T is going to be 42 minus 37 degrees Celsius. So my delta T is going to be 5 degrees Celsius. That's how much I've changed in temperature. Now, I can cancel out my units here, and I'm left just with kilocalories. 2 times 1 times 5, that's 10 kilocalories are expended to raise the temperature. Remember also, we gave this when we gave the definition of specific heat, that it takes 1 calorie to raise 1 gram of water by 1 degree Celsius. That's how we define the specific heat of water. How much energy is required to raise 1 gram of water by 1 degree Celsius? That's how we define the calorie. It's the amount of energy required to raise 1 gram of water by 1 degree Celsius. So you can think about this. I have 2,000 grams of water, and I want to raise them 5 degrees Celsius. It's going to be 10,000 calories, because each one of those grams of water will require 1 calorie for 1 degree Celsius. Okay, your book does an example, and we're not going to get deep into the math because as far as the math is concerned, you'll need to be able to do questions of this difficulty, which the numbers aren't that difficult here, but knowing which numbers to use, like knowing what specific heat is and knowing which formula to use, that's the hard part. But once you get the numbers written down, the math is not difficult. Okay? Yes, not bad. Y'all can do it. The hard part is knowing, all right, do I use the vaporization here or fusion? What's operating behind this phase change of material? Or knowing what is the specific heat? What is the mass? I'll give you those quantities, but I won't tell you which ones that you'll need to use. All right, let's consider a feverish person. With a 104-degree Fahrenheit fever. Y'all remember what is body temperature in Celsius-ish? 37. Rue, you don't get to answer. Yeah, so about 37. Because she's from Finland, and they use the Celsius system all the time. Right? Yes. Oh, yes. So, yeah, 98.6 is about 37 degrees Celsius. So anyway, we'll put them in an ice bath or a tub of water to cool. And I want to know how much energy must leave the person in order to cool properly. And I would say, well, Q is equal to MC delta T. This is similar to what we had before, actually. I have a person. People are about 70 kilograms. The specific heat of people is a little bit less than that of water. It's close to water. The specific heat of a person is 0.84 kilocalories per kilogram degree Celsius. And my change in temperature is going to be 37 degrees Celsius minus 40 degrees Celsius. This delta T up here, by the way, is equal to TF minus TI. In general, whenever I'm talking about a change in something, it's going to be the final minus the initial. With me, folks? Yeah. And so I can find the amount of energy. You'd probably need your calculator to do this. I would too. But it's going to be minus 176 kilocalories. The negative here, by the way, it's negative. The negative here denotes energy loss. Because Q can be either positive or negative. When an object is taking on energy, that is, its temperature is increasing, then I have a positive Q. If it's losing energy, its temperature is decreasing, that means that delta T is negative, because this number will be bigger than this number. When I have a negative Q, that means heat loss, not heat gain.
So Q is the amount of heat.
Q is the amount of heat, yeah. Q is heat. Or you can think of heat, it's the same as heat transfer. Because whenever we're talking about heat, we're talking really about the transfer of thermal energy. That I'm moving energy from one spot to another. You look back in your notes, you'll find that we had a similar definition. That heat is related to thermal energy, but it's not quite the same. It's the transfer of thermal energy. The way that we use it in physics. We use heat in a different way, sort of, as people. We just talk about it in terms of thermal energy. But really, it's the transfer of thermal energy. Alrighty? It's exciting stuff. Y'all look excited about it. Alright, let's look at one more example. This is from your book. This occurs through conduction. What occurs through conduction? Oh, so when we put the person in a tub, a person with a high fever, they'll lose that heat loss. The heat loss occurs through conduction. So, you know, you have a person in a cool bath, then they will lose that heat through conduction. And I can give you the various values, and I'll just do them here just as an example. But we've seen this expression before. Here, K, which is the thermal conductivity. Some materials just conduct heat better than other materials because it goes back to how their electrons are situated. Do they have a lot of free electrons? Conduction electrons, we call them. Metals have a lot of conduction electrons, so they conduct heat really well. Or are their electrons all bound up in their atoms? And in those cases, those electrons can't move around very well, and so they don't transfer energy as well. They're also not very good electrical conductors for the same reason. Here, K was equal to 0.2. That's for your body. Or it's really the rate of conduction between the body and the water. Oh goodness, I forget what the units are on that. A is 1.8 square meters. A is the surface area. Conducting heat. In this case, it's the whole surface area of your body. So your body has almost 2 square meters of surface area. You can think about it. I mean, my whole front of my body is about 1 square meter, and then the whole back of my body is about another square meter. So roughly 2 square meters. The book gave 1.8. Though remember, when we discussed this before, we had a slightly different setup where I had 2 objects, A and B, and then they were connected by some other material. And in that case, the only area that was relevant was the cross-sectional area of that connecting piece. Okay? This is just sort of the way we think about thermal energy and how heat is transferred in terms of this Q over T. That we have 2 objects, A and B. They have 2 different temperatures, and then they're connected by an object with cross-sectional area A and a length D. D here is this distance, but in your body, it's going to look like this. D, let's see if I can draw this. This is not an alien. That's a person. Okay? The person has an organ on the outside of our body, right? What's that organ? The skin. The skin is an organ. It's on the outside of our body. And we have that skin. I'll do it in a couple different colors. Helps to protect our body. So this space in between the blue and the black, that's our skin. And it has an average length, which in this case is D, equal to about 1 centimeter. Okay? So our skin is, on average about 1 centimeter. And that is the distance between the thing that is hot, which is the inside of your body, and the thing that is cold, which is the water outside of your body. So in a similar way, this diagram is similar to this diagram because I have object A outside the body, object B inside the body, and then they're separated by a distance D, which is the thickness of your skin, which on average is about 1 centimeter. That thickness, all right here, 1 centimeter, though we had converted to SI units to meters, but that's not important now. And then our change in temperature. Our change in temperature, if I have water, so let's say that T out here is 20 degrees Celsius, and so a cool bath, and here my temperature is 40 degrees Celsius, then my change in temperature is going to be 40 minus 20 are equal to 20 degrees Celsius. Okay? And then if we do that, if we calculate that, then we'll find then that Q over T is equal, don't do this with your calculator because we didn't change all the units, but we'll find that we're at about 720 watts. Remember, your body normally gives off about 100 watts of energy. It radiates away 100 watts of energy. But by taking a cool bath, you take away almost 7 times that, or more than 7 times that. That's why they put you into a cool bath when you have a fever. They've never done that to me. Anybody ever had that done to them? Really? Was it a really high fever?
It was 104.
104? Okay, yeah, it can be dangerous to have a fever that high for so long. I know my daughter, when she'll spike a high fever, she's sort of like me. She just has a high fever. She'll just have it for like half an hour and then it's gone. You had it for several days?
It was when I had the flu a few years ago.
Oh, yeah.
And I didn't get the flu shot.
Yeah, we didn't get it either this year. We got the flu. It was terrible. Anybody had the flu yet this year?
I had the shot.
Huh?
I had the flu shot. Yeah, but it wasn't bad with the flu shot. Like I ran like 99. It was not even fever.
Still felt miserable.
It wasn't that bad, not like the other time.
Really? Yes, I understand. All right. Then finally, we've talked about this, but let's just sort of get it in words. If you use more energy than you consume, your book talks about this. Then, let's see what happens. If you use more energy, then that's weight loss. You have weight loss. If you consume more energy than you use, then that's going to be weight gain. But you know, I mean, there's all sorts of factors that can contribute to this. High carb diets, for example. Can lead to weight gain. As the carbs are converted to fat. You can have genetic things going on with your body. Like some people are just, you know, they're sort of genetically disposed to be heavier. So lots of factors that can contribute. But on one end, it's just a simple math thing. Energy in, energy out. Alrighty? That's the end of that chapter. It's kind of an interesting chapter, I think. Any questions before we move on to the next? Alright, the next chapter we're going to be looking at waves. We'll look at different types of waves. We'll define certain things about waves, their velocity, their frequency, their period. Some of these might be familiar to you, but some of them will probably be new to you as well. And then in the second part of the chapter, we'll look at how the body produces sound. How we produce sound with our vocal cords, and sort of the effect of all the other parts of your body on producing sound, and then how we detect sound. How we detect sound with our ears. The ears are remarkable. They can detect sounds that are very, very low, like almost inaudible, and then they can detect sounds that are very, very loud as well. They can detect sounds that are very low frequency and a very high frequency. We really have no instrument that does what the ears can do, especially being able to do it for like 80 years effectively. So ears are probably my second favorite organ, next to the eye. But, so waves. We have lots of different examples of waves. We have waves in water. And these are, you know, we call these mechanical waves, by the way. When I have some medium that's moving up and down, we'll call that a mechanical wave. It'll turn out that sound waves are also mechanical waves, but waves in water are a good example of a mechanical wave. We can see like a slinky. I'll show you one here in just a minute, or a rope. Right, you ever have a rope where you just do this? There's a thing, like there's an exercise, you get the big ropes and you do the thing. If I just put a wave in a rope, that's a wave. That's a mechanical wave. It has a medium. The medium is the rope, right? Just like a water wave, the medium is the water. Have a slinky, you can have a rope, you can have sound. And then finally you can have light. Light is a different type of wave. It's an electromagnetic wave. I'm just going to write EM You don't need to know this. I just want to distinguish it from the others because light, we'll see in a later chapter, does not require a medium. Like all other waves will require mediums, but not light. Waves are periodic, I think. Yeah, periodic. That just means that they repeat. They repeat with a particular period. So they're called periodic waves. And that's all that periodic means. It just means that it repeats one after the other. And then a standing wave the wave travels back and forth through the medium and repeats so that it looks like the wave is not moving. Have y'all ever done the rope thing? What's that called when you have the ropes? Ropes? Yeah, so y'all know what I'm talking about? Like you have a rope at a fixed point, and then you have those two big old ropes, and then you do this thing. Y'all done it before? Yeah, it's a good workout. Like it's a good arm workout. It's sort of a good total body workout. But that's a good example of a standing wave. If you could do it just right, you have to do it just right. So if you have a rope, let's do it in black. Like this, and you make it go up and down like that, then you can create a situation where you have the rope appears to just be a single wave. Try that next time you're doing ropes, and try to get it so that you have it. It looks like the rope is not moving. You've done it before with like a hose maybe, or a rope in your yard. Yeah, maybe. I'll show you one in just a bit. But next time you're doing ropes, try that. Try to create a wave that appears like it's just stationary. And that's called a standing wave. I'll show you one in just a minute. I want to define a few things first. All right. Sound waves are periodic too. For example, a sound from a guitar. My son is learning to play the guitar. Dr. Will Robichaux is teaching him. Y'all know Will Robichaux? He was a doctor in town, but he's retired now. But anyway, he's teaching him to play guitar. And my son, he's only had one lesson, but he has been practicing a lot. So it's like he plays the C chord and the G7 chord, the C chord and the G7 chord. But he brought his guitar with us. He wanted to sit around the campfire and play his guitar, which he did, but he just knows 2 chords, and he doesn't really know anything else. But man, he's got those chords down. He has a lesson today, I think, and he's got those 2 chords down pat. You like play a musical instrument? What do you play, Kaylin? Okay, good. Anybody else? What does she play? The flute? My daughter plays flute. No, she plays clarinet. You play clarinet? No. I wanted to play clarinet when I was in school, but it wasn't really, it was considered to be like a girl's instrument. And I really wanted to play saxophone, but it was too expensive. My family just couldn't afford it. But the clarinet was like the next best thing, but then boys didn't play clarinets. So I played the trombone, and then I played tuba. Taylor, did you play something? Huh? Clarinet? It's a girl's instrument, huh? Is it? There are lots of great musicians who are men who play clarinet. There's nothing wrong with playing a clarinet. Adam, you play clarinet? Me too, tuba. Like that's a good man's instrument, right? Anybody else? Okay, well, we'll talk about musical instruments later because a lot of the properties of musical instruments, well, they're all built to create sounds of certain frequencies. And so we'll talk about what those properties are, whether they're a stringed instrument like a guitar or a ukulele or a piano, which is a stringed instrument, or a wind instrument, brass or woodwinds. Anyway, a sound from a guitar is periodic. It is a sound that just repeats over and over, like the C and the G7 chord, over and over and over and over. A clapping sound is also periodic. I mean, like that's also a periodic sound. I don't mean like this. I mean just like a single clap, but it just lasts for a very short time. We'll look at later in this chapter how some of these more complex sound waves are combined to create the sounds that we hear. Sound waves have a medium. That medium is air. They cause the air particles to move up and down, not forward. I'll show you a video probably next time, or maybe this time. But we'll see how these sound waves are produced, and you can imagine that if each of these dots represents air particles, these dots do not move like this. Instead, they'll move up and down. Actually, no, I'm sorry. No, that's not even really right. Why did I write that? Yeah, I'm sorry. Let me step back just a second. So, they move side to side. But not usually forward. Let me fix this in my notes. Okay? So when we look at sound waves, the air particle, like say I just take this little particle of air. Sorry to make you pull out your liquid paper. The air particle will move in this direction, but then it'll move in that direction. So we'll get these air particles that will move sort of within their sphere, back and forth, back and forth, back and forth. But like this air particle, for example, all of a sudden we're not going to see it just appear down here. That it's not going to travel along through to the next destination of the wave. So the air here that's around my hands doesn't travel to your ears. The energy does, but not the actual air particles. Okay, so we have two different types of waves, transverse and longitudinal. Transverse waves make the medium move up and down. And these are most waves that we think of. I like to think of it like the wave at a football game. Do y'all know how a wave at a football game works? Have y'all ever done this? So like we would come down here, and I'm the cheerleader, all right? So y'all be like this. No, everybody, come on now. And then I walk down, and then y'all do it, and then y'all do it, and then y'all do it. See, this is a transverse wave. This is a transverse wave where the medium moves up and down. And what's the medium in this case? You are, right? You're the medium. You're like the little particles of air. And you move up and then you move down as the energy moves through the medium. The transverse waves make that medium move up and down. So example is like the wave at a football game. And longitudinal waves, on the other hand, make the medium move side to side. And sound waves are an example of this. But I think that a good way of doing this would be to have, like the transverse wave, but that you would have a longitudinal wave at football games. And do you know what that would look like? Yeah, you would go side to side, but I'm going to call it not the wave, we'll call it the hug. And so like what would happen is like I would be right here, and y'all would hug one another. Hug one another. No, not the person behind you, the person to the side. Y'all ready? All right, go. All right, now this. So you don't have to hug one another. I'm not going to make you touch one another. But you get the idea that our longitudinal wave, the particles are going to be moving back and forth, or side to side like that, okay? The particles aren't actually traveling forward. Like Megan, you're not going to wind up over there where D is, but you'll move sort of side to side. Okay? You with me? Transverse and longitudinal waves. Let me show you. Look, I have this extra big slinky. It seems like it should. All right. So just hold it. I just need you to sort of hold it right there. Hold it from the very area. Okay? So this is just a slinky. Can y'all see it okay in the back? Taylor, can you see? All right. So I can create a standing wave. Remember, like with the ropes. Watch. There we go. See how it looks like it's not moving? You'll see that? And this, by the way, this kind of wave, is this a transverse or longitudinal wave?
Transverse.
Transverse, because the medium, which is the spring, is moving up and down. It's sort of moving side to side, but if I were to put it up like this, it would be moving up and down. You'll follow me? In contrast, this would be a longitudinal wave. You ready for it? Watch, because it doesn't last long. You see the longitudinal wave?
Yeah.
So in this case, the medium, it's like it hugs itself. Longitudinal wave. Now, we'll talk in a bit about period and amplitude. I'm just going to go ahead and show you this here. The amplitude is like how much is this wave displaced from the center position. So, my center position is right here. And now my amplitude is like right up here, my maximum amplitude. So I get an amplitude that's about 8 or 9 inches. Okay? Then also, we're almost. And then also the period is going to be the amount of time to travel a certain distance. We'll see that, but just sort of keep this idea in your mind that this wave, even though the particles don't move, but they just move side to side or up and down, even though they don't move, that they still have. That's good.
Okay.
They still have a certain speed that they travel. Not the particles, but the wave. So it's referring to the energy. Alrighty? Next time you're at a football game, you should do the hug. You get all of the people around you. If you're like an outgoing person and can, make people do things, then do that. Like get them to hug instead of doing this. Say, no, 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 no. Let's do a longitudinal wave instead of a transverse wave. Okay, simple harmonic motion. This just refers really to any oscillatory motion where the restoring force is proportional to the displacement. Now, let me explain it. This comes about, we usually use a spring to refer to this, that in a spring, I have a mass on a spring, that I have the force weight of the mass, and then I also have the force of the spring. And the force of the spring will equal to the weight. But it turns out that the spring force, this is my spring, the spring force, Fs, is equal to a constant times x, where x is just the amount that the spring is elongated. So I'll write that here. This is my elongation. Sorry, I sort of ran out of space. The more I stretch the spring, the harder it is to stretch. And that's true for you guys too. Like if you're in a medium, if I were to, you have a spot that you're sort of held into place by all the other particles of the medium. But if I took Megan here and I pulled her over here, the farther that she got from her desk, it would be sort of like she was attached to a spring. the farther she got from her desk, then if I let her go, then she's going to go right back to her desk. And the reason is because of all of you. Like, you're taking up space in the room, and you're exerting pressures. Imagine that you're a gas. Like, you're a gas, you see? All the other particles are exerting forces on her, trying to force her back into her position. Because you're a gas. And you have all this room sort of filled with gas particles. So, whenever I have air, then I have this simple harmonic motion, because if I disturb a particle that's in that material, then it wants to go back to its original position. And the more I disturb it, the bigger the restoring force is. So the restoring force is proportional to the displacement. F is proportional to x. That's just simple harmonic motion. That's really all that it is. And it'll be any type of oscillatory or periodic motion that we're talking about in this chapter. Several definitions that you need to know. The equilibrium position. This is where F is equal to 0. So if I have a spring, like this one, I'm just looking at the bottom part here. This is my equilibrium position. If I stretch it out, then I have a bigger force, and it's going to go back to that equilibrium position. Okay? So my equilibrium position is just where the restoring force is equal to 0. It's where that particle is at rest. I also have the amplitude. We're going to call this A. The period is the time for one complete oscillation. I'm going to draw a picture here off to the side, show you all these. And then the frequency is the inverse of the period. This is A, this is going to be called T, and this is a script F. So it's a normal F, but it has a little script on the bottom. If you just want to make it a normal F, that's fine. F is going to be equal to 1 over the period. It's just the inverse of the period. So, let me show you a graph. This is going to be called a history graph. And in a history graph, you need to know, I'll give you two different graphs. You need to know how to distinguish the two. In a history graph, what I plot is I plot on one axis, y, and then I plot on another axis, t, the time. And right here, this is y equals 0. That is my equilibrium position. At y equals 0, this is my equilibrium. If I look at a graph, or if I plot this graph versus time, it's going to look like this. So if I imagine on a string or something here, if I imagine my rope that as it's spinning up, back, or going up and down, I just pick one point on that rope, and then I follow the y displacement of that rope as it travels through time. So for example, if we were doing the wave, and y'all just kept going wave back and forth, then I would just look at Sydney, and I'd say, okay, where is Sydney now? Okay, now she's up, now she's down. Now she's up, now she's down. And so that's what I would plot on this graph. It takes the history of a particular point in the graph. I mean, the history of a particular point in the wave. You follow what I mean by that? If I have a rope, for example, my rope is moving up and down, up and down. Here's my person. If I'm doing ropes, what I do is I just take a particular point. And at some points in time, this is going to be up, and at other points in time, it's going to be down. It shows the history, the time history of that particular point in space. I can show the amplitude here. The amplitude is this, A. I also want you to show that this is also the amplitude. So often when we're measuring the amplitude of a wave, we measure from here down to here. And so that would be twice the amplitude. Sometimes that's just easier to measure it in that way, because we might not always have the origin drawn like I have it here. Also, the period goes from here all the way over to here. That's one period. I want you to notice here that I start here, and then it travels through one full cycle. That's one full cycle, and that's one period, one full oscillation. So remember, this is not in space, this is in time. So if I'm looking at Sydney, again, she would go up and then come back down again. She would start at where she is and then come back to her initial position. I'm not looking at the whole class, I'm just looking at one point on the wave and asking what's happening at that one point. And that's called a history graph. I can get from a history graph the amplitude, and I can also get the period. Once I get the period, I can find the frequency, which is just the inverse of the period. For sound waves, the speed is set by the medium. And frequency and pitch is related to frequency. We'll talk about this a little bit later, but first, the speed of a wave is, let me just write it, and then I'll have to define something else. The speed of the wave is equal to F times the Greek letter lambda. The Greek letter lambda is the wavelength. In order to show you the wavelength, I have to draw another type of graph. This is the second type of graph that you'll need to know. This is called a snapshot graph. Snapshot graph looks the same, but it's different. Your books talks about these. And this will be on the quiz next week, by the way. So on Tuesday, we'll have our quiz, and it'll cover some of this material plus some more. So make sure you read through those pages. The snapshot graph can look identical to the history graph. Right? That looks the same more or less. It's a squiggly line that goes up and down. But instead of having y versus t, what this shows me is y versus x. So I'm not looking at a particular point in time. So no longer, and Sydney, I'm sorry to use you, but no longer am I looking just at Sydney. Then I'm standing back, and at say t equal 2 seconds, I take a huge picture of the entire wave. And some parts of that wave are up, and other parts of that wave are down. So while Sydney might be here, then Jillian might be here during the wave. The point where Sydney is down, Jillian is up. So follow me on this? It's a different type of wave to represent the graph, but we use it because it can show us what our wavelength is. Our wavelength is the distance for one full oscillation. So on this graph, if I'm looking at the distance, my distance will start here, and then it goes through one full oscillation. So this distance, you all see that okay? Yeah, is one wavelength. It's the time for one complete oscillation. I go up, and then come back down again, and come back to where I was before. Notice, by the way, that I didn't do this, that I didn't come here and then just stop right there, because that's not one full oscillation. To have one full oscillation, I want to come back to the same point where I started, which is at the origin, and then coming up on the upslope there. I can show my wavelength in a couple different places. I can show it any places, right? I can show it, like I can start my wavelength here. That would be one wavelength. If I started it here, that would be one wavelength. All of those would be one wavelength. No matter where I start, I have to go through to the next identical point on the wave. Now, we know speed is distance over time. If the distance for one full oscillation is the wavelength, right? That's how we define wavelength. What is the time for one full oscillation? What's the time for a wave to go through one full oscillation? The period is right. So the time for one full oscillation is lambda over t, or is period. But I know that frequency is 1 over t. And so that's where I get this expression. Because this lambda over t, 1 over t is equal to frequency. So this is equivalent to the frequency times the wavelength. Let's just take a moment and look at our equation sheet. I'll come back to this. Let's just look at our equation sheet so we know sort of what we got and what we don't. Here we go. We're on chapter 4. Yeah, so here I have v is equal to f times lambda. That's our speed is equal to our frequency times our wavelength. Here's our definition of frequency, which is 1 over period. And then here is that more basic definition of speed, which is distance over time, or lambda over period, wavelength over the period. But these two expressions, f times lambda and lambda over t, they're the same. I'm just substituting frequency where I had 1 over t before here. Now, going back to that, I set up here that the speed is set by the medium and the frequency is related to the pitch. So high-pitched sounds have a high frequency, low-pitched sounds have a low frequency. Hey, I'll try this, see if you can do it. I've practiced this a lot, so you might not be able to do it, but with some practice, you might be able to do it. And it goes like this. Can you make, it's hard now, yeah. Low, high, low, high. Can you do that? Like make the sound of your voice different from the word that's coming out of your, try it. It's easy to go high, low, but go low, no, high, low. Can y'all try that? Yeah, think about it, try it. You got 20 seconds, try it. Yeah, it's like rubbing your belly and patting your head at the same time. Anybody? Did you just do it?
No, I don't
I've spent a lot of time practicing that just for this class. I don't do it for any other class because like y'all are my favorite class. But anybody? Anybody tried it? Sorted it out in their head? Low, high, low, high. Try it with your friends later. And say, well, you have to practice beforehand, but then show them, and they will be impressed. It's like, gosh, man, you are learning a lot in that Physics 151. All right. So this is true. V is equal to F lambda. That is true. But the speed of a wave does not depend on either the frequency or the wavelength. Oh, I'm sorry, does not depend. Depend on either the frequency or the wavelength. But you just say, no, because you just wrote V is equal to the frequency times the wavelength. So that doesn't make a lick of sense. Because you just wrote this. You said that the speed is equal to the frequency times the wavelength. But the speed of a wave does not depend upon either the frequency or the wavelength. It depends only on the medium. So for example, a high frequency noise will not necessarily have a faster speed. What happens here, V is equal to F times lambda. If I increase my frequency, my pitch, and what that does to the sound wave, it doesn't change the speed of the wave because this is always constant. It changes the wavelength. So if the frequency goes up, the wavelength goes down. If the frequency goes down, the wavelength goes up. Now let me draw for you, and we're almost done. I know you are eager to go, but draw for you, for example, two waves. One will be high frequency. That's a high frequency wave, and then a low frequency wave. See, big or small wavelength here? Small wavelength. Big frequency, small wavelength. Big frequency, small wavelength. Big frequency, small wavelength. Here, big wavelength, big wavelength, small frequency. Because a more frequent wave, that means it goes up and down more. More, like you have more oscillations in the same amount of time. Okay? We have a couple minutes. Let's just fill in these last things. In air, sound travels at about 340 meters per second. You don't need to know that number. I never asked a student what's the speed of sound, but, you know, impress your friends. And usually, in musical instruments, the larger the instrument, the lower the frequency. Like a tuba, for example. And that gets a little bit into what we're going to do in the next sections, talking about stringed instruments versus wind instruments and how the shape and size of those objects affect the frequency. Y'all have a great day. We'll start off with a quiz on Tuesday. I'll send you an email reminder, but be reading that chapter what, 4? Up through 114 or whatever it says. Great day, everybody.